Hello everyone, I hope you're all doing really well. I'd like to take a second to thank you for your patience and your cooperation during this semester. I can imagine that a lot of you are dealing with a lot, and I just want to let you know that if there's anything I can do to help you out, to support you, I'm here for you. Please send me an email and I'm happy to help in any way I can. The college does have information and resources in order to help students, and you're entitled to them as well. So please, if there's anything I can do, please send me an email and I'm happy to help you allocate whatever resources you may need. So today's lecture is going to continue basic statistics. We're going to be talking about norm-referenced tests and criterion-referenced tests, how to interpret scores. While you aren't going to be writing these tests or actually administering these tests, it's still something that's really important for you to be able to know so that you can help your students interpret tests, have an idea of how these tests are created, and also to help you make decisions for your students as they get placed into various kinds of programs. Just a quick note on standardized testing. When we talk about standardized testing, really we're talking about anything that's going to be administered and scored under a certain set of conditions. At some point, I'm certain that some of you have had some type of standardized test, and if you recall, there was probably a proctor that was reading instructions exactly the same way for everybody, and they had a fixed determined amount of time that administer these tests, etc. Standardized tests is anything that is, again, administered and also scored using the same conditions for everyone. There's different kinds of scores that are reported and also different kinds of tests. There's norm-referenced tests and there's criterion-referenced tests. Examples of norm-referenced tests, and I'm using NRT as the abbreviation here, are the SAT, the ACT, the Stanford Achievement Tests, ITBS. If you work for a parochial school or a private school, a lot of times you'll see the ITBS. As far as Criterion-Referenced Tests, which we abbreviate as CRT, they would be things like the Regents. So let's start by talking about norm-referenced tests first. So norm-referenced tests are professionally developed and reviewed. A lot of money and time goes into developing these tests. Right now, the SAT is created by the College Board, as well as, I believe, the ACT and some of the other sort of professional tests. Generally, norm-referenced tests have many items over a broadly defined content domain, so it's not on one specific skill or idea. It's kind of an integration of many, many things. And it's used to create an established set of norms to provide national comparisons as well as local comparisons. When looking at norm-referenced tests, basically the scores are providing information as to where the student ranks compared to other students. In some point, you might have heard that like SATs are norm-referenced tests, and the student's score is a function of how well they compare against other test takers that have taken that test on the same day. There is more than one factor that weighs into the student's score on that exam. It's not just what they got right, but also what other people got correct and what other people got wrong. Norm-referenced tests are only as meaningful to the extent that your student, for example, fits the norm group. This can be difficult to do if your student belongs to a special population. For example, students with special needs. National studies, which are the ones that you hear about like in the news, really focus on national norm group comparisons. And a lot of the times, these national studies or these national norm groups are what's being used by administrators within your school to make decisions about the whole school. In that situation, where decisions are being made to affect the students at your school or one student in particular, like if you were going to place a particular student in a program, in a specialized program, then perhaps it might be more important to look at local norms instead of national norm groups. They might give you more information of how well that student did relative to other students that are in similar schools versus students throughout the country. There are different types of norm reference tests that you might see, and I just want to mention this very briefly. You might see multi-level norm reference tests, which means that the tests are administered at multiple grade levels. This is something like the New York State's tests that the students take, like starting in 3rd grade. They take them again in 4th grade, and 5th grade, and 6th grade, and 7th grade, and so on. They could be a survey type of test, which means that the test is just very, very broad and general schooling rather than a specific instructional objective. Or it could be a battery of tests, meaning that the complete test is composed of many subtests. And we're going to see some examples of a battery of tests in a minute. Like, for example, the state test that the students take from 3rd grade all the way up to, I believe, 8th grade. That is a multi-level test because it happens so many times, every single grade from 3rd grade to 7th or 8th grade. But then also it's comprised of various smaller tests within that testing period, so it's also a battery. Norm reference tests have a variety of commonly reported scores. Some are very useful, some not so much. One that is not useful at all is the raw score of a norm reference test. It usually will tell you the number correct, but it's not interpretable because remember, the purpose of a norm reference test is a function of not only how well a particular student scored on the test, but how well that student did relative to everybody else that also took that test. Another commonly reported score is the percent correct. That's also not interpretable because, again, it doesn't really matter what the student scored or what percent they got correct on the exam when you don't know how other people did on the exam either. For example, if you had a student that scored a 90, and let's just say that they scored a 90% on the test, with just the raw score and the percentage correct, that doesn't tell you if 5 people did better than that student, 10 people did better than that student, 1,000 students did better than your student, 10,000. Like, you don't know exactly how they rank relative to others or how large that test-taking population is. So it doesn't give you any information on how well they did. So let's look at how this works mathematically. So in the last lecture, we discussed how data can be normally distributed. And as a quick reminder, we know that when data is normally distributed, the mean and the median are exactly in the center of the normal distribution. In order to work more efficiently, I went ahead and opened up this Ziteboard. I will link the Ziteboard in the description box below so that you have a better idea of what I'm drawing here. So, like I said, as a quick reminder, we've got the mean and the median that are exactly in the center. That's one of the indications that tells us we have a normal distribution. I'm going to go ahead and say that the mean is in the center, and let's just use the IQ scale. The IQ test has a mean of 100 and a standard deviation of 15. So if my mean is right here in the center, and this distance is my standard deviation, then I know that if I think of this as a number line, one standard deviation above the mean is going to have a corresponding raw score of 115. And if this is another standard deviation, then 2 standard deviations above the mean will give me a corresponding raw score of approximately 130. If I add another deviation, then I can say that 3 standard deviations above the mean, when the mean is 100 and the standard deviation is 15, I have a corresponding raw score of 145. Similarly, I can look at this by going in the opposite direction. This is also a distance of 15. If I have 1 standard deviation below the mean, I have a corresponding raw score of 85 when the mean is 100 and the standard deviation is 15. I can also say that this is another deviation that is, now I'm 2 deviations below the mean. So if the mean is 100 and the standard deviation is 15, then the corresponding raw score for two standard deviations below the mean for the IQ scale is 70. And finally, this last piece is another standard deviation. Now I'm 3 standard deviations below the mean, and so the corresponding raw score for 3 standard deviations below the mean on the IQ test is 55. Okay, awesome. So this is something we worked on with our last lecture, and I just want to put this up as a quick review. When we have a normal distribution, there are proportions that always exist within the normal distribution. So for example, and I'm going to go ahead and make this in red. So for example, if I look at this distance So if I look at the area underneath the curve for one standard deviation, I'm sorry, I'm really trying to draw this as neatly as I can. For one standard deviation before and after the mean, then if I have a normal distribution, and only if I have a normal distribution, then what always happens is that approximately 68% of all values exist within one standard deviation before and after the mean. Since this is symmetrical, I can say that 34% or is the probability for something to happen within one standard deviation below the mean, and another 34% is the probability of something happening within one standard deviation above the mean. Okay? And that would be a total of 68%. Within two standard deviations before and after the mean, then there is a probability of approximately 95% of something occurring, or a test in the case of the IQ test, of someone scoring between two standard deviations before and after the mean. So that would be a 95% total. Now we already know that this part is 34% and this part is 34%. I'm going to write total right here. But now there's an additional 13.5% in this part of this, in this area, and an additional 13.5% in this area. Within 3 standard deviations, and again, just to reiterate, I'm really sorry that I can't color very well. I promise that if I had crayons, I would be much better at this. I'm embarrassed at my coloring. I'm actually a very good colorer. Okay, all right. So, the probability of something occurring within 3 standard deviations before and after the mean is approximately 99% total. So that would mean that this part is still 34%, this part is still 34%, this part is still 13.5%, this part is still 13.5%, but now this part is 2.0%, and this part is 2.0 or 2%. Okay? Which means that anything left over, anything less than 3 standard deviations below the mean, is approximately 0.5%, so 0.5%, and anything greater than 3 standard deviations above the mean has a probability of 0.5% occurring. They would be extreme values, something that is extremely less than the majority of the group and something that is extremely greater than the majority of the group. I'm going to go ahead and fill out this diagram with all the probabilities so we have it as reference. So again, this part would be 34% of the curve. This would be 34% of the curve. This would be 13.5% of the curve. This would be 13.5% of the curve. This would be 2% of the curve. This would be 2% of the curve. And you would have 0.5% greater than 3 standard deviations above the mean, and 0.5% less than 3 standard deviations below the mean. Now this can also be added up from left to right. So I'm going to go ahead and just add this up slowly from left to right. Hopefully I can make this all fit. Okay, so let's just say I'm starting here at 0 and I start adding everything. Okay, just add it up 0.5%. Now I add up the probability of the next standard deviation, so I'm up to 2.5%. Now I'm going to go ahead and add the additional 13.5, so now I'm at 16%. Now I'm going to go ahead and add up an additional 34%, and I'm at 50%. Now that makes sense, right? Because here's the curve, half of it is 50%, so here 50% would be below the mean and 50% would be above the mean. I'm going to just scooch this down just a little tiny bit and keep adding. Okay. All right. So now I'm going to add an additional 34%, and I'm going to get 84%. Now I'm going to add an additional 13.5%, and I'm going to get 97.5%. I'm going to add the next standard deviation, and I get 99.5%. And then finally, I'm going to go ahead and add that very last piece, which is 0.5%. And I get 100% of the curve. Okay? All right. So now I'm going to leave this as it is, and I'm going to go ahead and jot down the same IQ reference raw scores that we figured out before. So I'm just going to put you on pause real quick and pop that up. Okay, so now I've gone ahead and set up my normal curve with all the corresponding pieces here. I'm good to go. All right, so let's just say a student scored, let's just say your students got 115 on the IQ exam. Remember, the mean of the IQ exam is 100, the standard deviation is 15, and your student scored 115. So that puts them right here. Very good. Well, with the normal distribution, we can actually say that the student scored better than approximately 84% of all test takers, but not as well as 16% as all test takers. So if we look at this right here, everything to the left, if we add up all these percentages to the left, we got that that student was scored better than 84% of all test takers. But not as well as 16%. If I had a student, and this time I will put the student in blue, okay, on this turquoise color. Let's just say you had a student that scored an 85. They're here. So the opposite is true for this student, right? They scored better than approximately 16% of all test takers, but not as well as 84. So the student in blue scored better than 16% of test takers, but not as well as 84%. Let's just say I have a student here in orange, and I'm going to go ahead and put this person right in here. In this situation, the student with a 70 IQ scored better than approximately 2.5% of all test takers, but not as well as 97.5% of all test takers. Now, if a student were to fall somewhere in the middle, you need some sort of technology to figure out exactly how well they ranked versus everybody else, but these are nice rough cuts that help you interpret the data. Another advantage to working with the normal curve and normalized test scores is that there is a standard reference used to discuss students relative to one another that is not dependent on the raw scores, and those are z-scores. So z-scores are these numbers that you see right here on this axis right here. These are called z-scores. The mean is given a z-score of 0. One standard deviation above the mean is given the z-score positive 1. 2 standard deviations above the mean is given the z-score positive 2, and 3 standard deviations above the mean is given the z-score of positive 3. So the positive is the sign here is basically saying that we're going to the right in the positive direction. The same is true of z-scores that are less than the mean, so that exists less than the mean. So 1 standard deviation below the mean has a z-score of -1. 2 standard deviations below the mean has a z-score of -2, and 3 standard deviations below the mean has a z-score of -3. So again, the z-score sign here in this case, the negative, gives you the direction that the scores are to the left of the mean. Okay. Now, the advantage of z-scores is regardless of what the mean and the standard deviation are, you can still get an idea of how well the students fared according to their z-scores. So I'm going to go ahead and pop in the raw score equivalents for the IQ into this model. So here I have gone ahead and just made everything fit the IQ test scores. I'll go ahead and write out as a reminder, the IQ test mean is 100, standard deviation of 15. Here, if someone were to say to you, a student has an IQ that is 3 standard deviations above the mean, without even knowing the scale, you know that this person is a lot higher, has an IQ that's a lot greater than the majority of the group. Right? They're way out here. If they have a 3 z-score on any test, that means that they have scored better than pretty much everybody. Everybody except for 5%. They scored better than 99.5% of the other test takers, and only 0.5% of students that have ever taken this exam did better than your particular student. So you want to, the nice thing about z-scores is you don't need any indication, you don't need any prior experience or knowledge of the mean and standard deviation in order to be able to discuss how well the students did relative to the rest of the group. In order to calculate z-scores, it's actually very easy to do. As easy as just sort of like lining it up and drawing this out, you can certainly do that. So for example, if I said using the IQ scale, what is the z-score of a student that scored 115, you can just say that their z-score is +1 because you can just kind of look at this. Let's just say a student scored 127. It's not something that is exactly in between. While we can't calculate the probability because you do need technology for that, you can calculate the z-score by using the z-score formula, which is just the student score, and from that you're going to subtract the mean and you're going to divide by the standard deviation. So in this case, if a student scored 127 and the mean is 100, and the standard deviation is 15, then you could just pop that into a calculator, and I will drag my calculator over so that we can work it out together. Here is my calculator. 17 divided by 15 is 1.133. The student has a z-score of positive 1.133. Okay, so that gives you an idea of, wow, that student's doing better than about 84% of all students. How can we do this? We have the rough cuts that will allow us to do an overall interpretation. It's not a fine interpretation, but an overall idea of how well the students fared relative to the other students in the group. Here's a reference, a very nice reference of how the percentages are distributed and what their corresponding z-scores are. Something like this is really nice to have if you want to snap a picture of this so you have it when you do any of the labs or on the final exam. It's kind of nice to have. I will also make sure that you have a copy of this in Blackboard, and I'll try to link it in the description box below. As far as test scales that you should know, the test scale that you would see often would be like the Stanford-Binet IQ test scale, and that one is the one that I've been using in my examples, which has a mean of 100 and a standard deviation of 15. The other one that you might see is the T-scale, and the T-scale is used for the PSAT. So any of you middle school teachers that use the PSAT, that one has a mean of 50 and a standard deviation of 10. So you would be able to set up your normal curve with 50 in the center and then just add up and subtract the standard deviations on either side of the mean. The other one that's used very often in education is the SEDF scale, which is the one used by the SAT. And that one is 500 is the mean score, and there's a standard deviation of 100. So for any of these, you should be able to just draw up a scale, or many of you might be able to do this in your mind, and be able to just give a rough estimation of how well students scored on any of the standardized scores. Percentile rank is another way that you can describe how well students did relative to one another. In this case, the students are just ranked in order from the lowest to the highest, and the scores are just divided into 100 equally sized groups. The lowest score in the percentile is a first percentile, and the highest is a 99th percentile. The reason is that because when you're interpreting a percentile rank, basically your percentile, or the percentile you're interpreting, tells you that that person, and we'll just say that student for now, that student did as well or better than that particular percentile group. A student that got 99%, it's saying that that student did as well or better than 99% of all test takers. The reason we don't have 100% is because you can't do as well or better than 100%. You can only do as well or better than 99% because you can't score higher than 100%. The mean of a percentile, the average of a percentile, can be very misleading. So you don't want to kind of look at the mean in this situation. Let's look at an example here of how you might see percentiles and how you might experience them in your work. So let's say that you want to help Jose interpret his scores, or you're using his scores in order to place him in some sort of specialized program. Either it's making sure that he's getting placed into an AP program, if he's getting placed into a remedial program, whatever it is. And Jose took 2 tests. One test was considered to be easy, and the other test was considered to be hard. On the easy test, Jose answered 95% of all the questions correctly. However, he's in the 64 percentile rank because so many students scored more than 95% on the test, right? So there's just a lot of people that did even better than him. On a hard test, let's just say that Jose got a 64%. If he scored in the 95 percentile rank for that test, it means that he did really, really well on this test. He did as well or better than 95% of all test takers. Even though he got low score, that's still much higher than what the majority of the group received. Percentile ranks are really easy to use, so it's really nice to use them for communication. Regardless of how comfortable anybody feels with mathematics, they're able to understand where the student ranks relative to someone else. A less commonly used reference score is called a stanine, and stanines are just even more rougher cuts to describe where students fare relative to one another. It's collapsed into 9 categories. Stanines 1 through 3 are considered below average. Stanines 4 through 6 are considered average. And stanines 7 through 9 are considered above average. So they're very coarse distinctions. I don't see a lot of stanine information, to be quite honest with you. I know that they do use them like in military type exams. So if for some reason you run into a student that got their scores because they're interested in joining the armed services, this might help you interpret that. But to be honest, I haven't ever seen stanines myself. If you wanted to just compare them to a percentile rank, this is more or less where they would fall. It does not correspond linearly. There's no proportional correspondence between the percentiles and the stanines, but it kind of gives you a better indication of how they compare relative to one another. This slide is just all the information on one slide. So if you notice here, we have the normal curve where it has its percentiles. If you notice, these are slightly different than the ones that I provided earlier. I kept it rounded just to make things a little bit easier for our purposes. These are all estimations. They actually go out several decimal places, so it's slightly different. These are the percentile equivalents, so it kind of gives you the idea of where students would fall percentile-wise. These are the corresponding z-scores. If you're using the t-scale, this would be how the t-scale lines up. Same with the SEB. Stanines, here would be how the stanine scale compares to the standard deviations or the norm reference scale or equivalents or any of the tests that we talked about, test scales that we talked about. The Wechsler scale, I believe, is an IQ test, as well as the one that's down here that, if I could just get this thing to cooperate with me, see the very bottom one is the Stanford-Binet IQ test. Grade equivalent is another way that you can describe student performance. The grade equivalent conveys the grade and months of school within a grade. So basically what it does is, if you can think of September being 0, the 0 month, October is the first month, so 1, November is 2, December is 3, January is 4, February is 5, March is 6, April is 7, May is 8, and June is 9. Okay, so that's how this is set up. What grade equivalent describes is it describes the level of performance on questions on that exam. If a student from that grade equivalent took that exam, they would have received the same grade equivalent. Say, for example, there's a student in 5.3. So that would be 5th grade, right? And then 0.3 would be the month. So September is 0, 1 is October, 2 is November, 3 is December. Okay, so 5.3 is a student in the 3rd month of their 5th grade year, so a student in December of 5th grade. Say they took an exam, and on their reading exam, they got a grade equivalent of 6.4. That means that they scored similar to the average 6th grader, basically a 6th grader in January, if that 6th grader came to 5th grade and took that exact same test. Let's look at the math score. In this situation, the student got a math score of 9.1. That means that if a 9th grader in October came and took that exact same test, then they would receive approximately the same score as this 5th grader did when they took the test in December. What's important here is that this does not describe skills or curriculum. This describes what's on that exam. The problem with grade equivalent is that it's created using some anchor items and some statistical estimation methods. So the transformations are kind of difficult to describe, and there can be some disparities within the grades as far as when standards change, and it can be highly susceptible to errors. It's often misinterpreted by people. So for example, if somebody has a fifth grader on math computation tests, they got a 9 something, like the example I just showed you, that does not mean that the fifth grader can do algebra, which is the curriculum that somebody might study in ninth grade. It means that if a ninth grader came into that fifth grade classroom and took that test for that fifth grader, they would have gotten about the same score. So it's basically showing that an older person, one that has had more experience and more education, can come into this student's class and score approximately the same as the student that actually took the test. Let's look at an example on a test record here. So I hope you can see this. If not, try to make your screen a little bit bigger. You can definitely zoom in. Let's see. It says, to whom was this test administered? Well, right here it says grade 4.6. So that means that this is a fourth grader and this is in their 6th month of school. Just to calculate this out, remember September is 0, October is 1, November is 2, December is 3, January is 4, February is 5, and March is 6. So this student took the test when they were in 4th grade in March. And it says, what is the student's national percentile rank and what does that mean? Well, their national percentile right here is 91. So as compared to the national norm group, this student scored as well or better than 91% of all test takers. What is the student's local percentile rank and how does it compare to the national one? Well, the student's local percentile rank is right here. They also have a 91% percentile rank. That means that as compared to local schools or local test takers, that student scored as well or better than 91% of all test takers. All we can really say is that when we look at the local percentile, the student is doing much better than most of the people in his local group, and the student is doing much better than most of the people nationally. So whether they're related or not, we can't really say. The student's grade equivalent is 6.8, which means that if a student in May of 6th grade came in and took the same test, then they would score about as well as this 4th grader did when the 4th grader took the test in March. So still very good. The student is not doing 6th grade work. They're just doing 4th grade work really, really well. One other piece that I want to discuss is the standard error of measurement. And we're not going to get into the calculation or anything like that. Basically, what I want you to take away from the standard error of measurement is that with any exam, there will be some level of error. With standardized tests, we can have some idea of what the student's true score is, but because of a variety of different reasons, and they're the same kind of reasons that we discussed when we discussed items earlier in the course, the test maker themselves, the test publisher themselves, cannot truly know the student's true test score due to random error. But what they can give is a margin of error where they believe the true score is most likely to exist. And they would show this estimation by a band that would extend on both sides symmetrically from what they believe the student's true score to be. So let me show you what this looks like. If you look over here where it has the stay 9, and here's the stay 9s down here. Is this the same student? Yes, it appears to be the same student. Notice here it has stay 9s at the bottom. Here it has the percentiles. Notice here there is a dot, and then there is a band that extends to the left and to the right, and this band is approximately the same length. So what this is saying is that this student, and this is their score in social studies, they believe that the student scored in the 91st percentile here. That's what they believe the student's true score to be. But due to error, they are willing to say with some degree of certainty, and I don't know what the degree of certainty is because it doesn't state it, but they're willing to state that to some degree of certainty, if the student's true score is not 91, then their true score does exist somewhere between 86 and 96 or something like that. And here it is right in through here where it should be 86 to 96 if I'm lining this up correctly. Okay. While they believe the true score is here, they can admit that there is some error in the testing process, and in the testing process accounting for that error, they know with some degree of certainty that the student's true test score exists within this margin of error. If you have a battery of tests, there is the possibility that these bands will overlap. But let's look at what I mean. So this is actually in your labs folder. You can find it in there. Here is the entire test. And again, I believe that this is that fourth grader that we used the test earlier. Here is his social studies band right in through here. Okay, so here's the social studies band. He received and I don't know, I'm just saying he, but whatever. I don't know who the student is. So he received a 91. His score was as low as an 86 and as high as a 95. I'm not exactly sure why this doesn't line up exactly, but here is the range that they're given. So this is how he scored in social studies. Let's look at the very first one because this one's easy to see. Reading vocabulary. In reading vocabulary, he also scored a 91 and his range is between 86 and 95. Okay? Because these bands overlap, we cannot say that there's any distinguishable difference between how well the student did in reading vocabulary and social studies. Let's look at language mechanics, okay, which is this fourth one. 1, 2, 3, 4. It's this one right here. In this one, the student scored a 70. Now, according to the standard error measurement, remember, the test manufacturer believes that this student scored a 70, but they could have scored as low as a 59 or as high as an 80. This does not overlap with their social studies, right? Their highest is an 80 for language mechanics, and the lowest for social studies is an 86. Because there is no overlap, we can say that there is a distinguishable difference between the student's performance in language mechanics and social studies. However, let's look at this one right here. In this one, which is study skills, the student scored a 96. They believe that the student's true score is a 96. The highest their score could be is as high as a 98 and as low as a 91. Okay? And as a reminder, their social studies score was a 91, but they could score as high as a 95 and as low as an 86. Because these two bands overlap, theoretically, they could have scored a 93 on both tests because that's within the margin of error. It's within that confidence interval. So you cannot say that there is a distinguishable difference between how well the students performed on social studies than how well they performed in their study skills test. Same thing is happening, this one, spelling, and let's just say this third one, which is total reading. Their spelling score is, they have a 72. The 72 is what the test publisher believes, or the test scorer believes that the student scored is a 72, but due to the margin of error, they could have scored as low as a 59 or as high as an 84. When you compare that to total reading, right, where the student scored in the 91st percentile and they could have scored as low as an 84 and as high as a 96, there is a distinguishable difference between those two, right? The highest they could possibly gotten in spelling, according to the margin of error, is a 94, where the lowest they could have gotten in total reading was a 86. So there is enough of a space there in order to say that the students, there is a distinguishable difference. So in summary, if the bands overlap, You cannot say that the student is better at one subject versus the other, or they scored better on one test versus the other. If the bands do not overlap, then you can say that there is a distinguishable difference between the two levels of performance on those two subjects or on those two exams. There's a lot less to say about criterion-referenced tests, so let me quickly just give you some characteristics. Instead of the test taker kind of competing against everybody that's taking the test at that one sitting, like on a norm-referenced test, the test taker is really just competing against the information that's on the test. They're up against the test, in other words. It's measuring a student's performance based on mastery on a specific set of skills or objectives that have been predetermined. They can also be called mastery tests, and basically the test taker has to exceed a minimum score called a cut score in order to pass the test. Like it's a pass-fail type of thing. An example would be the Regents exam. So I know that for some Regents exams, you also get some sort of like a higher level or some sort of like achievement honor certification on your diploma, but there is this cut score that everybody must exceed. So that's why the Regent exam the Regents exams are considered criterion-referenced tests. Another one is a driver's license test, where everybody has to hit a minimum score. You can only get X many wrong in order to still be able to get your driver's license. When you're comparing criterion-referenced tests to norm-referenced tests, you might think of it as just criterion-referenced tests just are looking to see, did this person get the answer correct or did this person get the answer incorrect? Versus a norm-referenced test where they are actually ranking the students based on how well they performed on that exam. In this case, the first student answered World War II was caused by Hitler and Germany invading Poland. According to the scorer, this person on this norm reference test, this person believes that the answer is worse than what student 2 wrote for the answer, but it's better than what student 3 wrote for the answer. So they're comparing the students' answers to one another versus just looking to see if the student got the answer correct. The stuff that we want to do in the classroom is we're not wanting to compare the students to one another. We are wanting for the students to demonstrate mastery against our objectives. The stuff that we do in our classroom is more alike to a criterion reference assessment than a norm reference assessment. In terms of the uses of standardized test scores, they should just be considered another point of information. So it should add information, not be the only metric upon which you make decisions for students. So it's okay to add information about individual students' strengths and weaknesses, looking at the curriculum as a whole and where students are having problems so that you could revise your teaching, setting instructional priorities about how you're going to look at the scope and sequence within your school to see how much time is allotted for particular subjects where students may struggle and how it may be appropriate to fall back a little bit on things that students are particularly excelling at, looking at the way things are being taught. But it's completely inappropriate to use this as a sole basis for anything that's going to affect students long term. So placing students in special programs, making retention decisions, judging the quality of the entire school, prescribing specific content to teach, or looking to place blame upon anyone about why students are not doing well in a particular subject. I know you're happy this video is done, but trust me when I say, I know that I'm even more happy that the recording for this video has been finished. I just want to, again, thank you for all your cooperation. If you need anything at all, remember I will be live in my virtual Blackboard for office hours, and I hope that you'll stop by and say hi. If you would like to set aside time specifically for yourself during those office hours, I'm happy to do so. Take good care of yourself.